So we started talking about this topic last time a little bit. And today and next time will be the meat of it. Today we'll talk about kind of how these systems work, how they evolve, what kind of assumptions we make, and how we use them. We'll start talking about how we use them to trace mixing between materials. Hopefully what was clear from the last couple of times when we talk about trace elements, it's really useful in tracking how things form. For instance, melting in the mantle and the style and crystallization, all that kind of stuff. The problem with them is that we don't really have a way of tracking when we look at variations within a magma or a series of magmas or the history of a volcano or variations within an individual lava flow. We'll see a lot of variation in trace elements, and we don't know if that's, did that all happen during this modern episode of petrogenesis, or is that something that was partly inherent in the mantle beforehand? Like you can imagine, you could have two different compositions of stuff in the mantle that are melting, they're different somehow, and you mix those things. And so this is where we use these things to help us. And I introduced you to these isotopic systems last time. All of these things have very long-lived progenitors. These are the daughter elements. In the case of lead, there's 3 different isotopes. We'll go through it again today. But the difference is that the progenitors, in all but one of the cases, have half-lives that are the age of the Earth or longer, meaning very slowly over a period of time, the amount of some isotopes of these things have been changing. And so now you can imagine if we have heterogeneity in the mantle, for instance, if the core forming event or the very earliest crust fractionated to some extent part of the mantle, and we've talked already about the idea of a depleted mantle when we look at potassium distribution in the crust and in various other reservoirs on Earth, then given a lot of time, if we change what we call the parent-daughter ratio, then the radioactive ingrowth into these daughter isotopes will reflect that difference. And so we can tell the difference between something that happened a long time ago and something that happened recently by looking at the concordance between the actual parent-daughter ratio, for instance, rubidium-strontium ratio in this case, and the strontium isotope ratio, which is reflecting the tiny integrated ingrowth of strontium-86 from rubidium. So the things I want to talk about first are what assumptions do we make about the initial Earth? And one of those assumptions is something called CHUR, which stands for chondritic uniform reservoir. And we've talked about that concept before, right? We talked about a chondritic Earth. We have a pyrolite model where we basically take the iron and the volatiles out of 90% of the material, and the iron goes obviously into the core. And then we add an additional 10% of chondrite back in. That model works for some of the radiogenic isotope systems, but doesn't work for others. And part of the reason for that has to do with the chemical behavior of these guys, right? So for instance, neodymium and its parent samarium, these are refractory elements. They're part of that early condensate. They're lithophiles. They don't go into the core. So just like when we look at chondrite normalized diagrams, we can look at the neodymium isotopic composition. The same is pretty much true for lutetium hafnium. Excuse me one second. I'll just turn this noisemaker off.
It's CNN. Trying to get a hold of you.
And so they have a nearly chondritic value. So we can take the value that we measure in chondrites and say, yeah, cool, that's what we think Earth started with. For some elements, we can't do that. Good example is the rubidium-strontium ratio. So both rubidium and strontium, they're over here, right? Rubidium is here, strontium is here. Those are volatile in the concept of when things condense on the Earth. They're late condensates. So we don't know that Earth started with its full complement of rubidium and strontium. So instead, we use a different model, which we call BABI, which stands for basaltic achondrite best initial value. And what BABI is basically finding really old meteorites that are not chondritic anymore. They're differentiated. That's why they're an achondrite. So these are like basalt, balls of basalt floating around in space that we think went through the same early differentiation process that Earth went through. And so I'll show you how we estimate this, but for rubidium strontium, we use that instead. For uranium lead, it's even a little bit more complicated because uranium, which is the progenitor of 2 of the lead isotopes, it's refractory. There's a third lead isotope, lead-208, which comes from thorium. It's refractory, but lead isn't. Lead is volatile and lead is partly siderophile. So with lead, we have a different way of doing it, which is we have multiple isotopes that we can track together in time simultaneously, lead-206, lead-207, and lead-204. And we make a separate estimate from very, very old materials on Earth that don't have any uranium and lead in them anymore, right? So they formed, they locked in whatever the lead isotope ratio was at that time. And since then, it hasn't changed because there's no uranium or lead. And so there's also a meteorite called the Canyon Diablo meteorite. It's an iron-rich meteorite with very little thorium and uranium in it that people use as the initial value for Earth. So in all the cases of these isotope systems, we have an assumption of where did Earth start, okay? And we can check that, and people have thought about it and revised this a little bit over time, but I have to say that since people started using these systems, which was sort of the 60s for strontium, and late 60s for lead, and the 70s for neodymium, and the 80s for hafnium, the value that we use for the initial value of Earth hasn't really changed all that much. And it makes sense in the context of materials that we find, really ancient materials, meteorite materials, et cetera, et cetera. Doesn't mean that we're 100% certain that Earth started with a uniform value for each of these things, just like we're not 100% certain that the mantle started with a single uniform chondritic value. But just like when we do rare earth diagrams or extended trace element diagrams, when we normalize by a chondrite value, in this case, we're not really normalizing per se, but we're subtracting the initial value of the planet off, so that then when we look at variations in the isotopes of these things, we're looking at stuff that happened since then, right? We're looking at the radioactivity. So we'll talk about that. And then at the end of the day, and this will continue in the next time, we're going to talk about how we can use the power of isotopes along with trace elements to talk about mixtures. So this is the time evolution of one of those systems, the rubidium-87 being the parent, decaying to strontium-87 system, right? And as I mentioned last time, we measure isotope ratios. They're easier to measure on the mass spectrometer. The abundances are more difficult to determine than the relative abundances of two different isotopes. So we normalize to strontium-86. Strontium-86 is one of the major isotopes of strontium. It's not radioactive and not radiogenic. It's just there. It was formed with the early Earth and it hasn't changed. Obviously, one of these elements that comes from nucleosynthesis and was thought to be uniform in our sun. So over time, and over long periods of time, because the half-life of this is quite long, the strontium-87 value will change in that reservoir because it's being produced by the rubidium, but the strontium-86 won't. Okay. Now, whether or not this is in lockstep, these two ratios depends on lots of assumptions, such as how long has the time been, how much variability was there in the initial value of this, was the system closed or open? The chemical exchange is one of the conditions we have for radioactive dating and for applying radiogenic isotopes, which is that if we have some material and stuff goes in and out of it, right, at different periods of time, then it's very difficult to track just exactly what happened to it because of the time integrated nature. So for instance, you got a parcel of mantle and every billion years something happens to it, and then we measure the 87-86 isotope ratio in it, it's going to reflect in a time integrated sense some fraction of what happens in each one of those events. The longer ago it happened in the past, the more of it will be reflected in this ratio because of the very, very long half-life of rubidium. Okay, so we can write out a decay equation. I gave you this equation last time, with just parents and daughters, right? P and N, and then P and D, and I also had the letter N for normalizing elements. So in that notation, this was D over N initial, and P over N. But here I'm showing to you now for specifically rubidium and strontium. So this is the radioactive decay equation. The parent times e to the lambda t minus 1 plus whatever initial strontium-87 was in our reservoir. Didn't start with 0. Okay, so the amount from decay, the amount that was there initially, times the decay constant times time in the exponent is going to tell us how much we have here today. And in normalized form, I just put an 86 strontium underneath all three. You're just dividing through. And as I say, on the mass spectrometer, this is what we'll measure. This is what we'll assume. We also measure this. We do have to measure that as an abundance. And then we can do various things with this. For instance, we can use it as a clock to calculate time. Or if we know time, we can use it to try and estimate how much this is varying from place to place in the mix. So there's lots of different ways to use this. If we want to use this as a traditional geochronometer, for instance, like to date a rock, one way to do that is to look at several different minerals from a rock. So let's say you've got a rock, a basaltic magma, it formed 5 billion, or not 5, 4 billion years ago, 3 billion years ago, something really long time ago. Then what's going to happen is that when all the minerals precipitate from that rock, they're going to get a different rubidium-strontium ratio on the basis of the distribution coefficients, which we've already talked about, right? Like some minerals, they don't like rubidium, they do like strontium. Feldspar is a good example. Other minerals might prefer rubidium over strontium, amphiboles, for instance. Other minerals might not like to have either of them in. Magnetite's a great mineral for that. So for instance, in that case, the minerals that don't have any rubidium or strontium are going to give us kind of this estimate, right? There's not going to have changed. Sometimes we don't find any minerals in our rock that have that. As you'll see in a second, we can make what's called an isochron diagram. We can look at the zero intercept at zero rubidium of that line to pull off the initial value. But if we have a mineral, a bunch of minerals that precipitate from magma at a short time period relative to this half-life, they all form an array in rubidium-strontium space, but they all should start out with the same strontium isotope ratio because the process of making those minerals doesn't fractionate or separate from each other. The two isotopes are the same mineral. Okay, so this starts out the same. This is different. Over time, the value in each mineral is going to change because they have different values of this, even if they have the same value of this. Something with a high ratio of that is going to have a higher ratio of this, and something with a low ratio of this, when it forms, will have a low ratio. So we can plot that up and make an isochron. This works great for some materials on Earth, and it works terribly for other materials on Earth for a variety of reasons. You could imagine, for instance, in a lava that comes up, and we've got some xenocrysts, some crystals that are from the country rock. It doesn't happen in a place like Hawaii, but go to Yellowstone or a place that erupts with continents. Once in a while, we pick up stuff from that continental rock. And if we do that, and we've got some minerals that are from the magma and some minerals that aren't from the magma, and they're all mixed in, then we're going to get a lot of variation in this and some variation in this that isn't related to the event that formed the minerals. So there's some gotchas, but I'm going to show you some sort of really good results of this. And part of them will be, how do we estimate the initial value of Earth, this Babby, for instance. Okay, so this is theoretically how an isochron diagram looks like. This is the rubidium-strontium ratio. At time zero, when we fractionate things from a homogeneous reservoir, we can get different rubidium-strontium ratios, all at the same initial value of 8786. And with time, these are going to evolve. The higher the ratio, the more this is going to change, right? Because we have more parent. And so these arrows represent time. This is time zero. This is some higher time, right? This is like a little bit higher, a little bit higher, a little bit higher. So this line keeps getting a steeper and steeper slope as time goes on. And you can, in fact, write out an equation for this line using that equation that I just expressed to you before, and we can get time out of the slope of this line, which is e to lambda t minus 1. So longer the time, the steeper the slope, and we can calculate that from this diagram. So this is called an isochron diagram. Okay. Now, we can use isochron diagrams for all sorts of stuff, but as I mentioned, they work best when a system is closed. We can sometimes identify that a system isn't closed with an isochron diagram. Let's say we got 4 minerals in our ancient rock. We measure up all this stuff, and someone spends weeks in the lab because this is time-consuming work. You got to chemically purify and separate, and then you got to stick them on your mass spectrometer, and you got to calibrate and standardize and make sure everything's working. The power of the university doesn't go off or flicker like it does. If you get through all that and you get your results and you stick them up on a diagram and you plot them up, you're like, oh no, 3 of my dots are on the line and 1 of them isn't. Okay, well, if one of your dots isn't on the line, it means it formed at a different time and or in a different place. And so sometimes we have ways of saying, okay, I'm putting it in my paper, but I'm noting that I'm not using that mineral. Sometimes they fall right on a line, which is great. Sometimes they're all over the place and you say, okay, I can't apply this system here because it's not working. Usually we would know that ahead of time because we can screen our materials by measuring this. Maybe not as precisely, but we have other methods where we can measure the total rubidium over the total strontium. We could dissolve up a bunch of materials and find the ones that we think are going to be good. Okay, so this is an isochron diagram for different basaltic achondrite, they're minerals from a specific basaltic achondrite meteorite called Geochemistry. Okay, and so here's our rubidium strontium ratio, here's our strontium isotope ratio, and it's a little bit hard to see, but see all these little dots? These are individual minerals in that meteorite. Olivine, clinopyroxene, orthopyroxene, magnetite, presumably are the primary minerals. Sometimes there's some other accessory minerals, maybe some zircon, for instance. These kinds of meteorites, remember when we call them achondrites, it means that they have already been differentiated on a meteorite parent body, meaning some planetesimal out there, maybe in the asteroid belt, that maybe originally accreted from chondritic material, but through collisions and processing, they've remelted, they've lost their chondritic texture, no more chondrite, no more chondrules in them, no more CAI inclusions, they look like basalts. So these represent the very end of the condensation sequence and the very beginning of accretion, right? And just like we find materials that fall to Earth that are iron meteorites that represent early protocore formation on planetesimals, we also find basalts that represent early crust formation. So the gist of it is that we put all these dots on this line, okay, and we can calculate a time from it. This one happens to be about 4.5 billion years. The decimal place is a little bit hard to see in this reproduction, but this is 4.5 times 10 to the 7th. We can actually make these measurements way more precise. This is a really early measurement from 1975. This decimal place is now pushed out almost 2 more. But in any event, these things conform to a line. So they tell us a few things. That thing came from a single homogeneous material. There wasn't any complexity. There wasn't any variation in time between when those things formed, at least at the level we can resolve with the long half-life of rubidium-87. And they sit on a line that tells us the age, and their intercept tells us the initial value of rubidium strontium. Okay, and so you can do this with a bunch of different meteorites. This is where we come up with this value for Babi, okay, which is this basaltic achondrite best initial value. So we use the assumption, whether or not it's correct or not, it seems to work pretty well for Earth, that Earth started out after it went through its accretion, after it formed a core, it had a proto-mantle, and it was just starting to make a crust, just like these meteorites represent. And we're going to assume that the Earth had a uniform value of this, the silicate Earth. We're not talking about the core now. Silicate Earth had that value. Now, what is the evolution of strontium on the planet? What we can look at is, again, this value of 8786, right? Okay, the strontium, this is the daughter and the normalizing element, and we're going to compare it to a bunch of meteorites now that we've determined their age in an independent way, okay? Usually uranium-like dating. So this is time in units of 10 to the 10th times 10 to the 6 years, which are, these are tens of millions of years. So this is a short compressed time scale. We've talked about that time scale around having a gas, making small particles in the condensation sequence, getting up through differentiation and making planetesimals as being of this order, right? Millions of years to maybe 10 million years. Okay, so now what we're looking at are different materials on the planet. Allende, which is a carbonaceous chondrite, Ador, which is another carbonaceous chondrite material. And you can, they're sort of described, excuse me, Ador is a achondrite material. Allende is a chondrite. And we can look at the difference in these values and try and understand them as variations that exist in the kind of kind of homogenization process that represents the end point of accretion for the planet. And what we see is that people have done this with more and more samples now, more and more meteorites, but they follow along an evolutionary line. Not all of them conform as simply to a line like this, but where the variation in 8786 can be thought of, may not be this, but it can be thought of as variations in time from a single homogeneous rubidium strontium value, right? You could also think about it as not as variations in rubidium strontium all at the same time. But when you plot up enough of these together, because the passage of time doesn't necessarily, if we have enough initial rubidium strontium variation, allow us to sit along the line, you can distinguish that. So, when you try to make estimates of the bulk Earth, where it started, what we call the bulk silicate Earth without the core, you can go through the same process for a bunch of different chondrites. and achondrites. And this is where we kind of derive this single value. This it's a little bit less than, but roughly 0.7 is a good number to remember. Because we're going to talk about some strontium isotope ratios in a second, what values we have in other places. And when we're looking at strontium isotope ratios, we're really usually looking in the 5th and 6th decimal place. That's where the business matters coming out of the mantle. Maybe also the 4th decimal place. And so we're talking about subtle variations, partly because the half-life of rubidium is so long that even if we have big changes in rubidium strontium ratio, they don't really reflect huge changes in the strontium 87, 86. So these are some evolution plots of different materials on Earth. So again, we got time here, but now we're talking about billions of years. So here's the present, here's the past. Here's the 87, 86 daughter normalizing element ratio, and here's Babby. And these are hypothetical evolutionary curves for different kinds of materials, right? So as it kind of explains through here, these evolutionary materials are for A are for different kinds of mantle. B is so A is sort of mantle that's been slightly enriched in rubidium. B are materials that have been slightly depleted in rubidium. Think about where this would apply when we talked about the formation of an early crust and the removal of potassium into that crust from the silicate mantle. We at that time talked about the formation of what was considered a primordial bulk silicate mantle and a depleted mantle that was left behind, the residue of that. So B would represent the residue. A would represent something that had a high rubidium strontium ratio, and we can use various ratios for that. And then line C represents a third thing, which is that at some point in time later, underneath a continent, we pull a magma out, okay? And that magma also has a secondary event where it fractionates rubidium strontium, and we can pick whatever rubidium strontium ratio we want for it, but this is just a typical ratio. This is how the evolution in time of that material is going to go. It's going to shoot off on a very different line. The longer we wait, the more this will vary as a function of this being different, okay? And the mantle that melt came from now has literally very little rubidium, if any, left in it. So the mantle that came from that secondary melting event stays pretty much flat. It's a little bit hard to see, but it just doesn't change. It's not going down. It's flat. It's just a kind of trick of the eye. That to me, that looks like it's descending, but it's a horizontal. So you can think about on an evolving planet where we know that we are continually taking melt out of the mantle and leaving behind residues. We're also subducting materials back from the oceanic realm into the mantle again. That includes seawater and sediment and ancient basaltic rock that forms up the ocean plate. That stuff re-enriches the mantle, and so in the mantle we end up having domains that are, there may be some stuff that's primordial, there's some stuff that's enriched, and there's some stuff that's depleted, and those processes are ongoing. They didn't happen just once, they're constantly happening. So we get a range of values out of the mantle, and it turns out when we use these values in a non-strict radiometric sense for geochronology, but instead to sort of categorize materials like, well, the depleted mantle looks like this, or the enriched mantle looks like that, or primordial mantle looks like that. We're really talking about a trade-off between the parent-daughter ratio and the time since the last event that affected the parent-daughter ratio happened. And so since there are a range of processes going on, we get a range of compositions. We characterize different materials coming out of the mantle as being in the category of depleted, or the category of enriched, or the category of primordial. As we'll see in a second using other isotope ratios, there's different types of enriched. Okay, there's several types of material in the mantle that are enriched through slightly different processes. We can't distinguish them with this isotope ratio, but we can with uranium lead, with samarium neodymium, and lutetium hafnium. We'll talk about those in a second, but it's important to recognize that we use these more like flavors, right? Vanilla, chocolate, strawberry, than saying, we have a precise time and parent-daughter ratio associated with the formation of those events. Okay, so now this is another system, okay? And, I'm sorry that these all come from the textbook I used to use in this class. And so some of these have time over, the present over here. Some of them have the present over here. This one here has time evolving this way. Or it's the last diagram, time evolved. Yeah, so, okay, so if you have the present and you go back into the past, in this isotope system, neodymium-143 is the radiogenic isotope. It is produced from samarium-147. Okay, this has an even longer half-life than the rubidium-strontium system. And neodymium-144 is the normalizing element. Now, because samarium and neodymium, they're both down here in the rare earths, and the rare earths are refractory elements, we have a lot simpler time with estimating the initial value of the earth. It's just chondritic, the chondritic uniform ratio. So we can look at the chondrite values for samarium and neodymium. We can look at their isotopic abundances, average those across chondritic meteorites, and say, yeah, that's where Earth started. Okay, so we have an evolutionary line where Earth starts here, right? So in the nebula, where we might have some variation in samarium neodymium ratio as things are condensing, they will evolve along a slightly different line. But at some point, once we put the materials of Earth together and accrete, then given the samarium neodymium ratio that we have at that time, Earth's going to evolve along a slightly different slope of line. And the assumption is that primordial materials on Earth are going to represent the time evolution of this line all the way through to the present. Right? If we never change the samarium neodymium ratio, then over time, the sort of 4.5 billion years of time, they're just going to evolve along a line where this daughter isotope can keep getting higher. The parent, the normalizing element doesn't change. Now, let's go and do something like making a proto-crust. And so we're going to enrich the mantle, enrich the crust, the melts, because these are incompatible elements. And we're going to leave behind a residue that has less of both of these things in it, less samarium and less neodymium. Now, the thing about this system, which if you have to refer back to the table I gave you at the end last time, in the rubidium-strontium system, rubidium is generally more incompatible than strontium. So when we take a melt off, we get more parent and less daughter. In this case, because samarium, and because of the way the lanthanides work, samarium is farther along, it's heavier and smaller, it's a little bit less incompatible than neodymium. Okay, so in this case, when we make a melt of the metal, we get more daughter and less parent, whereas for rubidium-strontium, it's the opposite. So in this case here, the melts that come off the metal evolve more slowly than the mature line because they have less parent. And the residue, the stuff that's left behind in the mantle, even though it's lower in concentration of both samarium and neodymium, has relatively more samarium, so it evolves more quickly. Okay, and the more we deplete it, the lower the concentration of both, the more this ratio will change, because in a relative sense, we've pulled out more neodymium than samarium. And so we'll see that we can compare isotopic compositions of materials and say not only when did we think the partial melting happened, but how extreme was it based on the range of values that we get out of it. So when we look at the neodymium isotopic composition, this one here we can measure even more precisely than strontium. We can measure it to the 6th decimal place for sure, and sometimes to the 7th decimal place. And so how we look at these values, since basically you end up with numbers, everything on Earth has the same sort of 5 decimal places and then a few little things at the end that are varying, is we plot them up in something called epsilon units. Okay, and what epsilon units are, just like when we talked about oxygen isotopic composition and we looked at variations relative to SMO or relative to PDB, we compare them to the value of a standard. Okay, the standard for the longest time used to be called La Jolla neodymium. It was developed in a lab where I was a graduate student. It's been run out, so now there's a new standard that people calibrate to. Part of the reason we use standards, just like for oxygen, is so that we can subtract out all the irrelevant ratio, part of the ratio, and just look at the part that's varying. The other part is that every lab measures this thing. We hope we all get the same thing. But if we don't, someone gets a different value, we can normalize out those variations. And so epsilon units are variations in factors of 10 to the 6th. Okay, so in essence, when we plot something up in epsilon units, we're taking the value that we measured in our material minus the value of the standard that we also measure, divided by the value of the standard times 10 to the 6. And so we'll get units of like 10, or as you can see them here, you know. And so the way these are plotted up is, and the values that are greater than 0, okay, are depleted, and the values that are less than 0 are enriched, and 0 is chondritic. So basically, it represents material like this. We're looking at essentially deviations from this line. Okay, so when we're in negative space, it means we're you know, somehow down here, excuse me, positive space is down here, negative space is up here. In epsilon units, these two things become flipped. Okay, so these are the names of some of the reservoirs that we have in our initial Earth. So BSE stands for bulk silicate earth, the chondritic uniform reservoir that we assume that works pretty well for neodymium isotopes, not so well for strontium isotopes. We can see how this again age moving from this is the present going back into the past. So we formed something and then moved it forward here in a chondritic earth, right? Any kind of material in chondrites is just going to move along this line, along the 0 line. The bulk silicate earth is going to evolve along a steeper line because it's got you know, a different samarium neodymium value. And then various reservoirs, various things like early continental crust. This is just, you know, that doesn't mean all continental crust formed 3 billion years ago. It's just you know, just an example. But continental crust being formed in a way that has more neodymium than samarium in it is going to evolve into a way where these values become less positive, and depleted metal that forms from it is going to evolve in a way that becomes more positive. Okay, so unlike the rubidium strontium system, where we get higher and higher 8786s the more enriched the material is, and lower 8786s the more depleted it is, we have the opposite here. The more enriched the material is, the lower the value, and the more depleted it is, the higher the value. Okay, and this tries to depict what happens with other processes happening on the Earth as well. For instance, taking material and resubducting it, right, is the source of these flavors of enriched mantle. EM1 and 2 stand for enriched mantle 1 and enriched mantle 2. They're not distinguished so much in rubidium and strontium isotopes. They're really distinguished in lead isotopes. We'll talk about them next time. There's another kind of material called high mu, which mu is the uranium-lead ratio. So these are all 3 different compositions that can be formed by sticking stuff back into the mantle by subduction, having that assimilated billions of years ago, and then making some mantle that looks different than chondritic material or bulk silicate material because it's spent some time at the surface of it. Okay. Now you can also, some people have talked about an early Earth that has different compositions than chondritic. And in theory, you can track all these things on a diagram and then calculate, well, what fields would we expect? And what rocks do we get out of them? And so you can see here now, there's a couple of compositions on here. Mid-ocean ridge basalts, they fit with either one of these models. They come from a depleted reservoir, just like we talked about when we did the calculations for potassium, and they work for this model pretty well. We also have some materials on the planet that we think, because they have high helium isotope ratios, the helium-3 is primordial, it comes from the solar nebula, and it's not really been changed substantially since. The helium-4 has been changed by radiogenic ingrowth, but it's primarily the 3-4 that we're looking at. There are some materials that are up on Earth that give people the idea that there might still be some original bulk silicate or chondritic material down there that is still being sampled, or at least was sampled in the past in places like Baffin Island. This is debatable. Other people have made the argument that some of the coincidences are just that. They're coincidences. There's mixtures of material. If you look at enough stuff, you can find something like, oh, well, it's got the value that we predict. Once you see how complicated the mantle is, and as I say, we'll talk about this more next time, you start to realize that it's pretty unlikely that there's any BSE material left on the planet. There's some high helium 3-4 on the planet, we know that, but there's mechanisms for removing that bulk silicate earth material and storing it in other minerals and having it be released later as an alternate. but as I say, once you get to a dynamic Earth, where you've got, a continuous distillation process of taking material off the mantle and a continuous process of sticking stuff back in, and rocks form from them, then you start to realize that each one of these lines that are drawn here as representing single points of time are actually families of processes. We could draw this point here or here or here, and the ensuing isotopic values are going to change because the slopes of these lines, the deviation from this, depends on how much we've separated the parent-daughter ratio, and we don't always separate at the same amount. Sometimes we do it a lot, sometimes we do it a little. If you recall, last time I talked about the role of garnet as a fractionating phase for the rare earth elements. Well, so imagine you just make two different melts, one really deep in a garnet stability field in the mantle below about 100 kilometers, and one really shallow. Those melts are going to have different samarium neodymium ratios. Now moving forward a billion years, the one that's got the lower samarium neodymium ratio is going to end up with a different value of 143, 144 than the one that has a higher samarium value. Okay, and so as I say, it starts to become very complicated. And what we do is we use this way of thinking to help us understand high neodymium isotopic composition materials relative to BSE are depleted and low ones are enriched. And by comparing the isotopic compositions of a bunch of different things, rubidium, strontium, neodymium, lead, hafnium, lutetium, etc., and because they all have different half-lives, and because time and composition evolve slightly differently in each system, we can sometimes disentangle those differences. Okay, so this is yet another system, the lutetium-hafnium system. So that one sits over here. Lutetium, the very heaviest of the rare earth, right? And hafnium is over here. It sits right next to the rare earth. Remember, the rare earths fit in between lanthanum and hafnium. Okay, so hafnium is a high field strength element. We talked about these elements a little bit before. High charge, small ion. It behaves in petrochemistry similar to niobium and tantalum, are two of its kind of similar elements. Lutetium being a heavy rare earth, +3 charged ion, the heaviest of the rare earths, the smallest of the rare earths. So we get a similar situation to samarium neodymium, but more extreme because they're chemically more different, wherein the daughter element is less incompatible than the parent. So just like the samarium neodymium system, this diagram has present here, the past over here. When we start to pull materials off of that, materials that melts become depleted in the parent relative to the daughter. So they grow into depleted values, and the corresponding mantle that's left behind, which has more parent than daughter in it, gets more radiogenic. So in many of us, who work with these things, prefer, instead of using the terms enriched and depleted, which is a common terminology in isotopic literature, is to say radiogenic or non-radiogenic, right? And that means something different for the different systems. In the rubidium strontium system, the radiogenic component is the melt, because it's got more parent and less daughter, and so it grows in more than the source material it came from. Whereas in the samarium neodymium and in the lutetium-hafnium system, the melt is the non-radiogenic component. It's the part that grows less quickly than the source material it came from because it has less of a parent. But in other respects, the lutetium-hafnium system works very similarly to the samarium neodymium system. The main differences being different distribution coefficients, different half-lives. And so they're oftentimes compared together. I'll also tell you, technologically, this one was the last one to come online. Hafnium isotope measurements are really hard to make by thermal ionization mass spectrometer, which was the traditional way that all these systems were made. We now make these measurements on something called a plasma mass spectrometer, using a plasma to make our ions. It's kind of revolutionized the business of hafnium isotope ratios, starting around the year 2000-ish or so. So whereas for these other systems, by the year 2000, we had tons of data. And for some of these systems, ICP-MS is better for them too, especially for uranium lead, well, arguably anyway, for uranium lead, and for samarium neodymium. For rubidium strontium, it's probably still better to make make them by the thermal ionization method. We have both kinds of mass specs in my lab here, and so there's a whole sort of chemical side to this, whole discussion, which I'm not going through today, which is all the hard work that went into developing the methods to measure these things super precisely. So just like the neodymium isotope system, in this system here, we're looking at really small variations in the 5th and 6th decimal place. And so to be able to do that, you have to be able to measure stuff really precisely. Okay, so when we take those isotope systems, right, and the rubidium, strontium, samarium, neodymium, and lutetium happening, we put them together and we plot up the same values from different materials on Earth, and we'll go through that, and what that looks like next time. We start to see some obvious trends in igneous rocks, families of compositions, like, whoa, what happens here in Hawaii? What happens in mid-ocean ridge basalts? What do we find in the continental crust? Okay, and what we find is that there are clearly reservoirs in the mantle on the planet that represent a family of compositions. The depleted mantle, right? It's not a singular thing, but it's thought to exist primarily in the upper mantle. And one of the reasons for that is we mostly see it represented in mid-ocean ridge basalts, right? Think about this 70,000 kilometer long globe encircling system that's pulling melts off the mantle from a lot of different places. Most of the compositions there are depleted. Not all, especially when a mid-ocean ridge approaches a hot spot like Iceland or something. That's a separate category. But most of those compositions are depleted. And we think that the upper mantle has largely already been stripped out of melt from the process of making continent. And so we get a family of compositions, okay? And these compositions are less radiogenic in strontium and more radiogenic in neodymium and hafnium than the bulk silicate earth model for the primitive mantle, for the reasons we just talked about. Then we also know we made a crust, continental crust. When we talk about the evolution of the crust and various people's models of that, it also didn't form at a single time. But if we go to different materials in the continental crust, right, of different ages, we've determined independently, usually with uranium lead dating, and we measure both their daughter isotopic composition and the parent-daughter ratio, we can try to back out something about, in general, the processes that form them, the melts that form them. And at this stage, we're talking about the igneous components of the continental crust. And what we see is, again, there isn't a singular composition or process, but there are a range of compositions that pull the radiogenic and parents and daughters, the radioactive parents and the radiogenic daughters, out of the mantle to make this, and they store them in the crust. Okay, and a lot of that stuff is still there today. We have a crust, we have those materials, they've been pulled out of the mantle and they're sitting there in the crust. We also know that we have the rock cycle, crust is being broken down and weathered, transported as particulates. Some of it gets into the oceans, it gets into ocean sediments. Ocean sediments, as part of a package of lithosphere, get down in subduction zones. Some of that sediment is scraped off and plastered onto what we call the forearc or the accretionary wedge. But some small fraction of it goes back down into the mantle. So we can reintroduce some of this stuff back into the mantle. Okay, and that's the genesis of enriched compositions. Okay, because we're taking stuff that was pulled out of the mantle some time ago, and in trace element space, we can't tell when something happened. We can just say that it happened. In isotope space, we can say when it happened. Because you can imagine if you took some magma and made a little component of continental crust today, and you somehow broke down that rock, like did this all in 1,000,000 years, there's not going to be any time for radiogenic ingrowth to have changed the neodymium isotopic composition or the hafnium isotopic composition. The parent-daughter ratio will have changed. If you do that same exact process 1 billion years ago, then the radiogenic isotope ratio will show a change because we've given it 1 billion years to reflect that. Okay. So we start to get this compositional heterogeneity. And so the simplest way to think about the mantle is 3 families of material. Primordial material, sometimes called BSE or PM standing for primitive mantle, depleted mantle, and enriched. Okay, and as I mentioned and showing you on that one diagram from White before, there are 3 main categories. Some people debate this. This stuff came out when I was a graduate student, and at the time I was like, oh, this is just like, I don't know, postage stamp collecting or sports card collecting, I still think that to some extent, people are always looking for the end member composition, meaning the most EM1 like or EM2 like. These are families of compositions that reflect different components of material being subducted back down. Something that is high mu has a high uranium lead ratio. And we know that the kinds of materials that are part of the subducting plate that have that are, for instance, carbonate sediments. They have a lot of uranium and very little lead. And the uranium lead ratio is called mu, with the Greek letter. Enriched metal 1 and enriched metal 2 are slightly different compositions that are enriched, not in the same way. They show up primarily in strontium isotopic composition and in neodymium isotopic composition. And again, probably represent different parts of that package. We've got the oceanic lithosphere itself, which is interacting with seawater. Seawater itself over time has evolved an extremely radiogenic 87-86 ratio because both strontium and especially rubidium have relatively long residence time in the seawater. So over Earth history, we've just been accumulating more and more rubidium, which decays to make more and more strontium. So if you take a rock that has interacted with some seawater, it can incorporate some of that radiogenic strontium and have a deviation from its mantle value. This is something that we talk about all the time here in Hawaii. It's like, so we see strontium isotope variations, and they're relatively small, but could those variations, we always assume they come out of the mantle, but we ask the question, could they instead have come from ancient lithosphere, right? So our volcanoes are erupting through Cretaceous age lithosphere. It gives them 100 million years of time to sit there and have seawater percolating through them, and all of a sudden you build some magma, some volcano on top of that. If that were the case, you would expect to see more perturbation in the places with a low magma flux that are early on in the process. Think Loihi or Kamaepuakana relative to something like Mauna Loa, which has been cranking the way it's been cranking for 1.5 million years, kind of burned a hole through the lithosphere. You're not really assimilating anymore if it were to happen. And again, we have ways of checking that. We can look at chlorine concentrate. There's other things you can look at, but the point being that seawater has a very radiogenic isotope ratio, and materials in the subducting lithosphere, whether they are altered oceanic crust or sediments of one type or another, also carry a very radiogenic strontium component back into the mantle. And we believe those are the sources of enriched mantle composition. Okay? And we will talk about these, is what some people call the mantle zoo, next time. Right now, I just kind of want to go through what are the processes through which these things are formed. Okay, so now I want to talk about the lead system. And I saved lead for last. Some people say it's the best. It's definitely the most complicated. And part of what makes it complicated is the chemistry of the materials involved. So unlike rubidium, which just decays to strontium, or samarium, which just decays to neodymium, uranium doesn't just decay to lead. It decays to a whole series of daughters, to a whole bunch of different intermediate half-lives and chemistries. Same thing with thorium, okay? And so in the intermediates, there are things like radiogenic helium, helium-4, there's radon gas, which is a gas. There are other isotope daughters, there are alkali metals like radium and francium. There are metalloids like bismuth and polonium. This is the focus of my area of research, not the uranium and the lead, but all the little business in between. I use those things to tell time because they have relatively short half-lives. So we can look at things like how fast did that magma that's being erupted today at Mauna Loa form in the mantle. And so, for instance, I use lead-210. That's another metalloid here. It's not on the list. 22-year half-life. We can see signatures in lead-210 that tell us that melts, form, and transit off the mantle, and timescales really short to 100 years, like decades. They can come up those 100 kilometers, for instance. But so in these systems, they're a little bit more complicated. If you're going to do uranium lead dating, you have to assume that not only is the lead and the uranium unchanged since the stuff formed, but all the things in between are also unchanged, right? And so, yeah, there's a lot more complications with it. The benefit is that, for instance, in the uranium lead system, we have 2 different isotopes of uranium decaying to 2 different isotopes of lead with 2 different half-lives. And in cases where both of those things can form, meaning the isotopic compositions appear to reflect a closed system over the 2 different evolutionary time frames, then that gives us a lot of power. We don't even have to make the same kinds of assumptions that we do with the other systems. So these are the 3 actinide decay chains. And just to remind you, the actinides sit down here right below the rare earths, right? So thorium is below cerium, uranium is below neodymium. In some ways, they're very similar, right? They're bigger. They're a whole other electronic shell below. Lead is way over here. Okay, so it behaves very differently in these systems. And you can see here the way the decay is depicted. So these are the, excuse me, the atomic numbers. And so they decay and get lighter and lighter as they go. There's a couple of different kinds of decays here. There are alpha particle decays, which are helium-4 nuclei. Those are the ones that represent these diagonals that go down. And then there are also beta decays, which are these smaller steps. And I know it's a little bit hard to read here, but you can look at it in the notes, the half-lives, right? So this is 4.5 billion years for the progenitor. This is 713 million years for the progenitor. This is 16 billion years, okay? And then when you get down to these little things, these are the various daughters. Some of them are really short. You know, as I mentioned, lead-210, which sits here, 22 years. Polonium-210, which is another thing I measure, 138 days. We use this to look at processes happening during eruptions. Radium-226, which is another thing. Like my first Nature paper was about this, 1600 years. In a system that is closed, meaning no chemical exchange, all of these things are decaying at the same rate. You might say, how is that possible? They have different half-lives. The way it's possible is that the amount of material that is present at any given time is different for the different isotopes. The shorter the half-life, the less of it you need to sustain a certain decay rate. We have to think about it as you cannot have more decay of something than the thing it came from, right? It's like a supply and demand. If you have one thing that produces another thing and another thing and another thing, right? If you take the thing away up at the top, then the stuff beneath it's going to drain out, right? And so it's hard to produce extra daughters. You can do it instantaneously, like you could separate, make a material and separate a phase and have more daughter than parent in it, but over time it's going to relax back down to having a decay rate the same as the progenitor. The other thing I kind of want to point out is that the ends of each of these chains are different isotopes of lead. And it turns out that the lightest of these things, thorium 232, makes the heaviest isotope of lead, 208. And then uranium 235 decays to make lead 207. And uranium 238 decays to make lead 206. I also think back when we're talking about nucleosynthesis and the formation of the elements, the odd even thing applies here, right? So that we have more thorium 232 and uranium 238 in our original solar nebula than uranium 235. This is an odd isotope. So we've got a lot less. This is a minor isotope. Now add to that the fact that this half-life, this is about the age of the Earth. So we've lost about half of our uranium 238. This is longer than the age of the Earth. We've lost very little of this by decay since Earth formed. This one here, you know, 700 million years, we've lost a lot of it. So now if you think about it, over time, the ratio of 238 to 235 on the bulk Earth has been going up. Both individual elements are going down, but this one's going down way more quickly. So the time evolution of materials, we now start to have the ability to separate stuff out. If you take stuff off the mantle really early in our system, like 4 billion years ago, you start to deplete the mantle, you're going to see a big signature in this because there was a lot of this around. Okay, but if you wait to make your continental crust to 1 billion years ago, a lot of this stuff started to decay away. So the relative variation in lead 207 compared to lead 206 changes in time. And this is part of why the lead isotopes are so powerful. Now, in all of these cases, we normalize, just like we do with samarium, neodymium, or rubidium, thorium, we normalize to another isotope of lead that is stable and not changing, and that's lead 204. So you see, we'll talk about the 206-204 ratio. That somehow reflects the time integrated uranium lead ratio. The 208-204 ratio reflects the thorium lead ratio. Does that make sense? Okay. So we have that same situation where we can write out an equation. The daughter today was the initial amount of daughter in a material plus the parent times e to the lambda t minus 1. And it's a little bit more complicated in this case because, again, lead is volatile and siderophile. So it's very, very difficult for us to figure out the initial value for Earth, we can't just take a chondrite and say, oh, what's the lead isotopic composition there? In fact, there's a lot of heterogeneity in chondrites for that. So instead, just like we did for strontium, where we looked at the basaltic achondritic model, here we look for materials that have very little uranium or thorium in them that locked in a lead isotopic composition early in time. And those are end up being iron meteorites. And then what we do is to test that assumption, we compare those compositions to really, really early formed galena ores, galena being a lead sulfide, that if we could go into the continental crust and we could find little pockets of galena that are 4 billion years old or 3.5 billion years old, they also don't have any uranium and thorium. So we can compare their isotopic composition to some independent age of when we think they formed, such as the age of their host rock, to this initial value that we measure from the meteorite, and people have kind of honed in on this value that we use here. So we always use the same value for that. So this is the time evolution of the radiogenic ingrowth component of the lead isotopic composition. That is oftentimes depicted with a star. Okay, and all the star is taking the lead isotopic composition, doesn't matter which ratio you use. You could look at parent-daughter, I mean, you could look at, daughter to normalizing element ratios like 207, 204, or 208, 204. Or you can look at the two different daughters from these two chains, and if we look at the 206 relative to 207, right? They both come from uranium. We don't have to worry about uranium lead fractionation. If the system has been closed, then the only variation is time, right? The effective time, because a long half-life and shorter half-life. So instead of looking at the bulk 206, bulk 207, we just look at the radiogenic component, meaning the part that has had the initial value subtracted off. So thinking about it in this equation, we could rewrite this thing, right? Where we pull the initial over here, and the value that we're really interested in is the D star, the part that has been produced since it formed. D star is always going to be D today minus D initial, right? Just like pull this over. And so that's what we're looking at on this next diagram. It's the evolution of the starred value for the kind of lead that comes from uranium-235 and the kind of lead that comes from uranium-238. And there's only one single unique value here for a material with a single uranium lead. And it follows along this line. And again, starting in the present and going back into the past. And what you see is that in the past, that ratio changes more quickly. The reason the ratio changes more quickly is because back in the past, there was more 235 around. So in a relative sense, we grew more lead 207. Once we come forward into time, we ingrow more 206 because the 207 is already depleted. Okay, and so the values of this, as I say, you can look them up in the table. Everyone uses the same values. They come from the Canyon Diablo meteorite, and which is kind of described here. Now, there's a couple of other sort of assumptions that go into making these calculations, and the primary one being that we have a closed system. That something hasn't gone on to separate our isotopes. And like if you imagine you're happily decaying some uranium-238 along and it's producing all this stuff, but it happens in a case where volcanic gases can be stripped off, then the radon is going to be stripped off. If we lose some radon, then it's not going to keep decaying down the chain and we're not going to get this stuff. So we have to be careful about that. There's some radon here too, or there's radon in both of these systems. So if it happened to one, it would happen to the other. But sometimes we get complications in these systems because of things like that not being closed. There can also be other processes that happen, for instance, in the mouth, metasomatic fluids that migrate. They're like very, very small degree wet partial melts. We see them reflected as melt inclusions in diamonds, for instance. They can carry around a lot of uranium because they have CO2 in them, and uranium makes a complex with CO2. So it's also possible there are ways to make compositions in a mantle that violate the closed system parameters, but there are enough materials that seem to conform that that we're confident in this approach. And the ability of using two different isotopes that come from the same, two different isotopes of the same element that would be affected by the chemistry the same way, and being able to predict what the lead isotope evolution would be gives us a lot of power. That's why people do this kind of analysis. So these just happen to be the values for Kenyan diablo meteorite. You're not going to use them or make any calculations. But if you were to ever be presented with a data set and had to make some calculations, this is what you subtract off as the initial value. Okay, so now let's think about materials on Earth. Okay, so here we're plotting the lead 207, 204 versus 206, 204, the uranium 238 progenitor and the uranium 235 is progenitor, 204 is a stabilized. So we could make these plots with the star, and I would prefer them to be made with the star, but traditionally they haven't been made with the star. I don't know why. So these are unstarred, right? That's why primordial Earth doesn't start at a point of 0, 0. This diagram would be at 0, 0. Instead, these are the actually measured values in a sample. And so you can see here something called the geochron. The geochron is the family of compositions that represent Earth with an initial single value of uranium and lead, which just evolves over time. All of these other curves represent a family of these curved things with different values of uranium lead. And as I mentioned before, when we're talking about high mu as a composition, mu is just the uranium lead ratio. So this is an evolutionary curve for uranium lead ratio of 8, of 9, and 10. You can see they initially go up quickly in 207 and don't change so much in this, shorter half-life, longer half-life. And then over time, they turn over where pretty much only this is changing because we've depleted most of the uranium-235 by 8. Okay. We can take materials from Earth, like these galena ores, for instance, and plot them up. And if they plot anywhere to the left of this line, okay, we call them conformable lead because they are consistent with values of uranium lead that we find on the planet. Imagine if you found a material that lied on this side of this line, it would have an age. These are isochrons. This is today, 1 billion years ago, 2 billion years ago, 3 billion years ago. It would imply a negative age, which is impossible, right? So in the initial thinking about the way Earth worked in the initial, meaning the 60s, people thought that they would measure lead isotope compositions that only sat over here. It turns out there's a bunch of lead that sits over here, right? Which means that you can't explain it with a single stage of evolution. I jump ahead. These are the so-called conformable ores I was just talking about. These are lead ores taken from the continental crust at different times. These are the isochrons, meaning the present, 500 million years ago, 1 billion years ago, going back to 3 billion years. These all sit on a single uranium lead ingrowth parabola, right? One of these U lines. And they all sit to the left of the geochron, so we call them conformable ores. I added in a little spot over here for what are called unconformable ores, which are things that have negative ages, right, because they sit to the right of the geochron. But our assumptions about primordial lead and our assumptions about, at least for these samples, how they form, fit with all that stuff I just talked to you about. Now, it turns out that those unconformable ores, and we have some of them, but even more importantly, mid-ocean ridge basalts also all plot in an impossible space on that diagram, are impossible because the planet didn't evolve the way that diagram assumes. It didn't evolve with a single point in time of separating reservoirs depleted and enriched. It's a continuous process. And that continuous process shows up really well in the lead isotope compositions. So this is the next most complicated model, sometimes called Stacy-Kramer, where in essence we start out with primordial lead, we evolve it along a single uranium lead line, single mu, and then we allow a second event to happen. Okay, and since that second event happened some period of time, in this case, almost 1 billion years after Earth formed, 0.8 billion years. These are times and billions of years. Most of the 207 ingrowth is already slowed because our 235 is decayed away. So we get an array that's a lot flatter. So whereas the initial array, and you'd have to plot them up together, the single event array would kind of plot up like this. This extends compositions into much higher 206, 208, because we separate out another reservoir and allow it to start evolving at a later period of time. It's a hypothetical scenario. In fact, what's probably happening is it's a continuous thing. We're getting a family of compositions. It's still happening today that helps explain compositions that are so-called non-conformable. These are some examples of some non-conformable leads. That's the geochron. These are mid-ocean ridge basalt. They sit way out here in space with really high 206, 204 relative to their 207, 204. They formed from a material that was already depleted in uranium-235 and yet still had some uranium-238 in it, so it could produce the high 206, 204. And people have taken mid-ocean ridge basalts, this is relatively early data, and plotted them up and seen that oftentimes, if you take mid-ocean ridge basalts unaffected by hotspots, which have another component of isotopic heterogeneity other than the depleted metal in them, then you plot them up on isotope variation diagrams like 207, 204 versus 206, 204. I've also included the 208, 204, which is the thorogenic lead, for comparison. You oftentimes see that they fall along a simple line. You can interpret that line as time, and people have, and they're wrong. But in the distant past, they interpreted that as a time and said, "Oh yeah, it looks like all the mantle that makes mid-ocean ridge basalts all formed about 2 billion years ago, and therefore all the continental crust formed about 2 billion years ago." Because you can mathematically determine that from this line. Like I say, it's wrong. It's a mix. These lines are mixing lines. They represent some mixture between very depleted mantle and less depleted stuff that's mixing back in. And the more data we have, the more we realize that they don't all conform to a single line as we might expect. But in any event, the line has no time significance. It's really just looking at mixture of materials with different compositions in this space. We'll talk about it more next time. So, we have no evidence for this 2 billion year global event that you get from these lines. But in any event, we start to see compositional complexity that is revealed by lead isotopic composition that reflects time, reflects when stuff happened, much better than we see it in the rubidium, strontium, the samarium, or the lutetium lead system, the lutetium happening system, specifically because the half-lives are shorter here. Okay, so now we don't have much time. I just want to introduce this topic, which is how do we use this time variance and compositional variance of the radiogenic isotopes to help distinguish mixing processes, meaning mixtures of materials in the mantle that might have been sampled to make a suite of igneous rocks, or mixtures of materials that may have been put together to make a compound magma. And the way we do it is by looking at variations in the radiogenic isotopes and the trace elements together. To do that, we have to understand a little bit of mathematics of how mixing works. And so I kind of wanted to go through that first. And I just want to illustrate that with the ingrowth in the rubidium strontium system. So let's say we have a system where we just got some material, let's call it Babby, it's in the mantle, and it's closed. Nothing happens to it. We don't melt it, we don't add anything to it, no subduction or whatever. Then the rubidium strontium ratio is going to be going down because of decay over time, right? And the 87-86 strontium ratio is going to be going up by decay over time. But these values are going to be in lockstep. I'm trying to depict them with colors in the sense that we can account for all of our rubidium and strontium. When we add these two things together, the sum of these things is constant. We have an open system where, let's say we add some rubidium or we subtract from rubidium, it doesn't really matter which. Depending on when we do it in this time process, I've done it between step 1 and step 2, we get a chemical disequilibrium between the parent and the daughter, which will persist forever. Okay? If we give it enough time, the more ancient this fractionation was, the more likely this new event is going to be reflected in the final ratio we measure today. If we do a separation of rubidium and strontium yesterday, the strontium 87-86 ratio is not going to have time to reflect that because of the very long half-life. So the longer in the past that we do a compositional variation, the more similar the value that we get here and the interpreted value of what that implies for this and the measured value of this are. Okay, so that means we can use strontium isotopic composition to help us understand relative to rubidium strontium when fractionations happen. And so you'll oftentimes see people making comparisons of the 87-86 or the medium isotopic composition or the lead, whichever one you want, with trace element ratios and log. Because the trace element ratios and logs reflect that all the things that have happened to it all the complexity of what happened in the mantle and the magnegenesis and everything else. And so it stands to reason that if we see a lot of variation in this with this, then the variation that produces this happened long enough ago for it to be reflected by this. Whereas if we have a homogeneous material with a single 87-86 ratio, and we melt it in various ways that might fractionate our trace elements, and then we make mineral phases that might fractionate them, we might see a lot of variation in this with no variation in that. A good example of that is the Honolulu series rocks that are around us. Tons of trace element variations because of extremely small degrees of partial melting, but they all have really similar sorin isotopic compositions because it was the process of melting that made that heterogeneity. So I'm just going through these last couple slides, which is just about the mathematics of mixing, and then we'll pick this topic up next time. If we take two materials, I should say, a component A and B, and they have different chemical compositions, okay, we can depict their mixing. And so in this case, for this could be chemical A could be rubidium, and chemical B could be strontium or whatever. Mixtures between those two things, right? It could be two solid chunks of rock, it could be magnets, all two rocks. They follow along a simple line, and they're explained by this mixing relationship, which is basically just the concentration of A in the mixture is going to be B in the mixture times these factors, which are basically the relative proportions to the two things. It's just an algebraic sum, okay, of the two components. When it's very hard to disentangle variations on a diagram where everything lies on a line. And so instead, we oftentimes make more complicated plots where we're looking at more things like we look at the ratio of A to B versus B, or the ratio of A and B to a third thing like C, right? And so I don't know, you might already be realizing from last time, for instance, 87-86 strontium ratio and rubidium strontium ratio, right? Where component C could be like our normalizing element or normalizing isotope. We get these kinds of variation diagrams. Even more complicated, we could plot A over B ratio versus B over D, right? Lanthanum samarium ratio over thorium ratio or something like that. We get slightly different mixing arrays. And the mixing arrays in cases like this and like this depend not only on the concentration ratios between the two, but also the absolute concentrations, right? So you can imagine if you mix things where the concentrations of A and C and B and D are the same in both of these two things, they're going to mix differently than if, let's say, component 2, the thing we're adding in to component 1, has really high concentrations of this, or high concentrations of this and low concentrations of that, or vice versa. We can get different shapes of these parabolas, and small amounts of mixing can move us closer or farther from 1 to 2 along these mixing trajectories as we add stuff in. So I know some of this is a little bit perhaps non-intuitive, but the point being that we can plot up compositions on diagrams and we can make calculations of different scenarios and see if mixing scenarios of different compositions fit different things. Then we can add in a time component, which is, okay, let's do the thing way in the distant past, or let's do it today, and we can compare how mixing works for isotope ratios that involve radiogenic isotopes relative to trace element ratios that haven't been changed. So I'd say we'll pick up this conversation next time. We'll look at mixtures, and then we'll also look at the so-called mantle zoo and some of the isotopic heterogeneity that we have on the planet. Sorry for the whirlwind. They're always a whirlwind. Are there questions?
Yes, Sarah.